Yeah.
Yeah, today we are going to discuss our first chapter. Yeah, electric charge. Yeah, generally, if we rub two objects, there will be a transfer of charge between the two objects. So one will acquire a positive charge and another will acquire a negative charge. In this transfer of charge, what will happen? Like electrons from one body will transfer to the other body. So as electrons have a basic of negative charge and protons have positive charge. As the transfer of electrons transfers a negative charge from one body to another body, the body which transfers electrons from itself acquires positive charge and the body which gains these electrons gets negative charge. This is the basic phenomena occurs while we rub two bodies, like we rub a silk cloth with a plastic rod. The appearing of charges on the both bodies is a consequence of this process. Yeah, conductors and insulators. Generally, conductors are the objects which will be able to transfer the electron, which will allow the flow of electrons through it and conducts electricity is known as conductors. And insulators are objects which doesn't allow the flow of electrons through it is known as insulator. Generally, basic properties of electric charge. Electric charge has three basic properties. Additivity of charges, charge is conserved, quantization of charge. Additivity of charge means like we can add all the charges, like total charge on your body is sum of all the individual charges present on the body. That is additivity of charge. Charge is conserved. Like charge cannot be destroyed and cannot be created. Like in the process of transferring the electrons from one body to another, the total charge on the bodies will be conserved. Like initially, the total charge on both the bodies is zero. While rubbing the two objects, one body acquires a positive charge and another body acquires a negative charge, but the total sum of both the charges will be zero. That is, total charge is conserved. Quantization of charge. Like generally, whatever the object has a charge, it is the integral multiple of the basic unit of charge. Like generally, the basic unit of charge is the charge of an electron. Electron is the basic charge in the world. Like every body has an integral multiple of charge of an electron. That is quantization of charge. Yeah. Now Coulomb's law. Coulomb found that the force between two charges will be dependent on the charge magnitude of both the charges and inversely proportional to the distance between the square of inversely proportional to the square of distance between the two charges. That he found out the magnitude of charge to be F equal to K into Q1 Q2 by R square. If both the charges have the same charge, the same magnitude of charge, then if the both charges have the same sign of charge, like if both the charges are positive or negative, then the force between the two objects will be repulsive force. The both charges are opposite in nature, means one is positive charge and another one is negative charge, then the force between the two charges is attractive. Like now to find out the charges forces between two different forces due to different charges present in a vicinity of a charge, we will use the superposition principle. Like we can individually add all the forces. We can individually to find out the total sum of forces of all the charges. We can add the forces due to the individual charges at a single point, and we can find the magnitude of the net charge on a particle. I mean on a charge. Yeah, electric field is generally charges create electric field. Like a charge at a vicinity creates a field around itself, which will in return acts as a force on another charge present in the field. Like this is the electric field. If we multiply this field with the charge present in the vicinity, then we will get the force acting on the charge. So the force acting on a charge is a consequence of the field created by another charge. So for electric field is Q by R square. Force equal to charge into electric field. F equal to Q into E. Similarly, we can use the superimposition principle to find out the net electric field at a point. Like for finding a net electric field at a point, we can use individually calculate the field due to every charge at this point and just geometrically, like vectorically adding all the fields, we can find the net resulting field at that point. Yeah, generally field lines will be radially outward from a positive charge and radially inward to a negative charge. Generally, the field line, the direction of electric field will be parallel, will be tangential to the direction of like field line at a point. So never, so two field lines will never intersect. So that the field at a point should be unique. They should not intersect at a point. If two field lines intersect at a point, then it will result in two tangential directions which will not occur in a natural electric field. In a electric field. From a positive charge, electric field lines will be radially outward, and for a negative charge, electric field line will be inward, radially inward. Electric flux. Flux is integral E bar dot df bar. Like df bar is the area vector at that point, at that location of the surface. E into df. D phi equal to E dot delta S, where delta S equal to area ds into cos theta, where theta is the angle between the normal and the electric. This is the normal to the surface, and where E is the electric field in this direction. So total flux equal to E into delta S into cos theta. Flux is indirectly we call as the electric field which intersects through the surface perpendicularly to the surface. Like if we find the net projected area of the surface perpendicular to the field, we will get that ds into cos theta. So E into ds into cos theta will be the total flux linked with the surface. Electric dipole. Like generally we till now we discussed about the single charges, point charges. Now we will discuss about dipole. Dipole is a combination of a positive and a negative charge separated by a small distance. Now electric field due to a dipole is individually calculated by both the charges. Like initially we will calculate the electric field due to this point positive charge q and the negative charge minus q, and we will neglect the distance between, as the distance between the two charges is very small, like r is very less than, very greater than a. So we will finally approximate this expression into this form. We will neglect a square with respect to r. So we will finally result in the equation E equal to 4qa by 4 pi epsilon naught r3. It is the direction magnitude of electric field parallel to the dipole at a distance r. Yeah, dipole moment is P equal to magnitude of the positive charge Q into distance of separation between the two charges, the positive and negative charge. That is dipole moment. Generally, dipole moment equal to P equal to Q into D. If we want to calculate the torque acting on a dipole placed in electric field, that is P dipole moment P cross E, where P cross E is the scalar product of dipole moment and the electric field. That is the torque acting on the dipole moment. Continuous charge. Like till now we discussed about the point charges that are discrete in nature. But if we want to calculate the field created by a body which has a continuous charge, we will simply use the terms as charge density. Like charge carried by the body per unit area, or a line charge carrying per unit length, or a volumetric charge rho, charge carrying per unit volume. The basic formula is D equal to K into dq by r square. So from that we can integrate over the, like we will take a point charge on the body and we will find the field due to this point charge at a location, and we will integrate the charge around over the body, and we will find the net electric field due to the body over that point. Gauss law. Like this is one of the important concepts in the chapter. Like flux linkage due to a body. Like we will first like if we take a point charge at a location, to find out the electric field at a point, we will imagine a Gaussian surface, like generally symmetrical surface. In this case, we assume it as a spherical surface through which we will calculate the flux linked by the surface due to this object, and that we will get as d phi equal to E into ds. We will generally this electric field you created by this charge at this point will be kq by r square. Kq by r square into the area of this sphere will be 4 pi into r square. So we will finally get the flux, total flux linked with the surface will be q by epsilon naught. So the flux linked by a closed surface will be charge enclosed by the body by epsilon naught. So flux has two formulas, that is integral E bar dot ds bar, or is flux equal to integral E bar dot ds bar equal to charge enclosed by the Gaussian surface by epsilon naught. So that we can relate the we can easily calculate the electric field from this Gauss law. Generally, in finding the electric field due to a long cylindrical, like long wire, straight rod or long plate, we will use the Gauss law. For finding the electric field due to a straight wire, we will imagine a cylindrical surface and we will calculate the flux link at a point and the charge enclosed by the surface from the linear density of the line charge and into the length of this line charge will result in the charge enclosed by the cylinder. So we integral E bar dot ds bar, where ds is the surface area of the cylinder that we imagine, into ds bar will result in the charge enclosed by epsilon naught. So lambda into L by epsilon naught equal to E into 2 pi RL, where LL gets cancelled and we will result in the formula electric field due to a line charge will be sigma by 2 pi epsilon naught R. Similarly, for calculating a electric field due to a slab, we will by infinity plate plane sheet, we will imagine a surface and we will find the electric field through the charge enclosed by the surface. Now we will quickly go through the exercise problem. What is the force between two small charge sphere having charges of 2 into 10 power minus 7 coulombs and 3 into 10 power minus 1 minus 7 coulombs, and place them 30 centimeters apart from each other. Like we know that the force, electrostatic force acting between two charges will be kq1 q2 by r square. So we have the following information: q1 equal to 3 into 10 power minus 7 10 power minus 7 coulombs, and q1 is 2 into 10 power minus 7 coulombs, and q2 is 3 into 10 power minus 7 coulombs. And the distance r equal to 30 centimeters. So we will try to do everything in SI. So 0.3 meters. By substituting the values and calculating, we will result in force F equal to 6 into 10 power minus 3 Newton. Now we will go to the second problem. Like the electrostatic force on a small sphere of radius, a small sphere of charge 0.4 microcoulomb. Mu means micro. Due to another small sphere of charge minus 0.8 microcoulomb in air is minus is 0.2 Newton. What is the distance between the two spheres? What is the force on the second sphere due to the first sphere? Yeah. Initially they gave the force 0.3 Newton, 0.2 Newton, and the charges are 0.4 microcoulomb. 1 micro means 10 power minus 6 coulomb. Four into 10 power Q1 is 4 into 10 power minus 7 coulomb. And Q2 is minus 0.8 coulomb, minus 0.8 microcoulomb, so minus 0.1. So by using the equation F equal to KQ1 Q2 by R square, we can get the relation R equal to root over hello. Hello. Hello.
Yes, Gunavardhan. Please.
Sir, like, for getting the square root, like It's not there in the bold.
Get me the
Like it's not the square root is not there in my board. Keyboard. Like can I solve using a pen and on the paper? Okay. It will be more useful.
which one is the most appropriate?
Like can I solve it on paper?
Uh, if you are not able to solve properly, then you can explain well. If you are not able to write properly, then you can
Oh,
explain well.
okay.
Okay. So explanation is most important than writing. And
Hmm.
if you are not able to write properly, then you can explain well, so a student can understand.
Hmm. Okay.
Yeah. Okay.
Like again using the formula F equal to K Q1 Q2 by R square. We have force 0.2 Newton and the Q1 this 4 into 10 power minus 7 Coulomb and Q2 is minus 8 into 10 power minus 7 Coulomb. Also we have the value of K equal to 9 into 10 power 9 into 10 power 9 Newton meter square per Coulomb square. So, so by using all the three unknown, uh, by using all the three known and four known values, we can find the R number. R from this formula. Now we'll proceed with the third question. Also, there is a B part of the question that what is the force on the second sphere due to the first sphere? Like generally this force is mutually interactive with both the charges. So whatever the force acted on the first charge due to the second charge will be equal to the force acted on the second charge due to the first charge. The magnitude of forces will be equal acting on both the charges due to each other. But the direction will be different. It will be opposite to the each other. Third question. Check the ratio of Ke square by GME MP is dimensionless. Look up a table of physical constants and determine the value of this ratio. What does the ratio signify? Yeah, yeah, we know that electrostatic force will be KQ1 Q2 by R square. Also, we have gravitational force. Let us say Fp is electrostatic force and Fg is gravitational force. Gravitational force will G m1 m2 by R square. So let us say we will take one proton and an electron. Let Q1 and Q2 be the charges of the proton and electron. So here in the Q1 and Q2, like M is mass of electron and MP is mass of proton. So we know that mass of electron will be 9.1 into 10 power minus 31 to 10 power minus minus 31 K. And mass of proton will be mass of proton will be 1.67 into 10 power minus 27 kg. The value of K is 9 into 10 power 9 Newton meter square per unit. And the value of G, universal gravitational constant, is 6.67 into 10 power minus 11. Ten power minus 11 Newton meter square per kg. Newton meter square per kg. So if we divide FE by FG, we will result in, as the charge of electron and proton will be charge of electron equal to minus of charge of proton, as both are negative and neutral. So K into charge of electron, K into charge of proton minus E. Like where E is the charge of electron, whole divided by R square gets cancelled, and G into mass of electron, Me into mass of proton. This is the ratio given in the question. K square by GMU into M. That is the value of force of electrostatic force by gravitational force acting between a proton and an electron. This is the magnitude. Like actually, we are getting a negative sign here. It means the electrostatic force is also a magnitude of proton will be within the same heat. So we will finally get the required equation K square by GME equal to electrostatic force by gravitational force acting between a proton and an electron. By using the following values, if like charge of an electron will be 1.602 into 10 power minus 19 coulomb. Ten power minus 19 coulomb. So by using the equation, by using the value, we will get that FE by FG equal to 2.4 into 10 power 34, 39. This signifies that the electrostatic force in this range of distance bit will be very large, 10 power 39 times larger than the gravitational force acting between the two particles. Export. Explain the meaning of statement electric charge of the body is constant. It means that the electric charge of a body is quantized. Like generally, every charge is quantized, so the charge will be an integral multiple of a basic charge, that is the charge of the electron. So charge on a body will be an integral multiple of charge of an electron. Like why can that is the meaning of the charge of an electron. Charge of a body is quantized. Why can one ignore quantization of electric charge when dealing with macroscopic, that is large scale charges? Like this means that when the charge of a body is very large, the charge, as we know that Q equal to N into E. So as the charge of an electron is, as the charge of a body is so large, and the order of the charge of an electron is so small that it is 1.602 into 10 power minus 19, then the value of N will be so large. So even in a small change of like transferring of electrons, the value of N won't be changing much. So in large case, the macroscopic charge, the quantization of charge will be neglected. And we are going to the question. When a glass rod is rubbed with a silk cloth, charge appears both. A similar phenomenon is observed with many other pairs of bodies. Explain how this observation is consistent with the law of conservation of charge. As know if the as we discussed that charge is conserved, charge on one body will be transferred. Charge on one body is transferred to the other body. So one body will retain positive charge and other will retain negative charge. Whichever body loses the electron will retain positive charge, and whichever body will gain the electrons will retain the negative charge. Now we are going to the fifth question. For point charges QA, QB, QC, QD are located at the corners of a square ABCD of side 10 cm. What is the force on the charge of 1 microcoulomb placed at the center of the square? Yeah, like let us assume this is a square. And this is side layer. B. C. And D. And charges are respectively placed on the corners QD, QC, QB, and QA. And now we assume that a charge of 1 microcoulomb is placed at the center of the plate. That is draw the diagonal AC and BD. Yeah. At this center point, he placed a charge of 1 microcoulomb. As the distance, let us say the center as point E. Yeah. Now he told that as he placed the charge at this point E, that the distance AE and EC are equal, and the charges placed at A and C are same, like 2 microcoulomb and 2 microcoulomb. So the net electric force acting on the point E will be repulsive due to the both the charges. So the force acting on the AE will be in the direction of EC, and the force acting on E due to C will be in the direction of EA. So both the forces will be cancelling each other. So magnitude of both the forces due to the force due to the charge A equal to force due to the charge C. So both the charges will cancel out each other. And also the force due to the charge, as the charges both D and D are equal. So the distances ED and EB are also equal, as the diagonals in FY are bisected each other. So ED and EB also equal. So the force due to charge B equal to force due to charge B. So the net charge on the force on the charge, the net force on the charge will be, so the net force on the charge will be 0. Well, that's what is the question. An electrostatic field line is a continuous curve. If a field line cannot have sharp break, why not? Yeah, generally this electric field line is a continuous curve. As we discussed that if we place the electric charge in an electric field, it will move in a continuous manner. So it should be acted with a continuous force. As it is acting as a continuous force, that we know that F equal to Q into E, the field should be continuous. It should not have any breaks. I'll explain why two field lines never cross each other at a point. As we already discussed that the electric field will be in the direction tangential to the field line. So if two different field lines cross each other, then the it should have two different tangents at that point. It represents that it will have two different electric fields at that point, which is not possible. So two electric field lines will never intersect each other at a point. Two point charges QA equal to 3 microcoulomb and QB is minus 3 microcoulomb located at 20 centimeters apart. What is the electric field at the midpoint of the line AB joining the two charges? As we know that formula for electric field is KQ by R square. Formula for electric field is KQ by R square. What is the electric field at the midpoint? So as both the charges are negative in nature, so the net electric charges will be double of the electric field due to a single charge. So electric field E equal to KQ by that the distance between the charges will be 20 centimeters located 20 centimeters apart. So R will be from both the charges are equal to 10 centimeters from each of the charges, and Q is 2.5 into 10 power 7 minus 1 coulomb. So we'll use the formula KQ by R square for both the charges. Minus Q by R square. As the direction of both the charges will be different, which will result in these 2 into KQ square by KQ by R square. By substituting the values, we will get, as we have the value of K is 9 into 10 power 9, 9 into 10 power 9, Newton meter square by Coulomb square. By substituting these three values in this equation, we will get electric field as 54 into 10 power 5 Newton per Coulomb. Fifty-four into 10 power 5 Newton per Coulomb. This is part A, and part B If negative test charge of magnitude 1.5 into 10 power minus 9 coulomb is placed at this point, what is the force experienced by the test charge? Yeah, we found the electric field as 54.54 into 10 power 5 Newton per coulomb, and the given the charge is minus 1.5 into 10 power minus 9 coulomb. As we know that the force due to an electric field is F equal to Q into E. So by using both the values, the value of charge and the value of the electric field, we will get the force as minus 81 into 10 power minus 4 Newton. Into 10 power minus 4 Newton in the direction of D. Yeah, as you know that the electric field and the force, all these quantities are vectors. Yeah, we're going for the ninth question. The system has two charges, QA and QB, located at points minus 15 in the z-axis and 15 plus 15 in the z-axis respectively. What are the total charge and electric dipole moments of the system? Yeah, as you know, the dipole will consist of a positive charge and a negative charge. Here the value of QE 2.5 into 10 power minus 1. 10 power minus 7 coulomb. And the distance between the two charges is plus minus 15 and minus 15 is 30 centimeters. Yeah, they asked about the total charge. So the total charge will be Q total equal to Q positive minus Q negative equal to total charge will be 0. The total charge will be 0. And again they asked about the electric dipole moment of the system. Electric dipole moment P equal to Q into distance between the two charges. We have the value of Q as 30 centimeters. Q as 2.5 into 10 power minus 7 coulomb and distance is 30 centimeters. So that if we calculate the value, we will get the dipole moment as magnitude of dipole moment as 7.5 into 10 power minus 8 coulomb meter. Yeah, as you know that the dipole is not a scalar, it's a vector, so we need to find out the magnitude of the dipole, the direction and magnitude of the dipole. We found the magnitude of the dipole as 7.5 into 10 power minus 8 coulomb meter. So then into the direction vector. Okay. For R bar. into R cap. As we know that both the charges are lying in the z direction, the R cap will be in the dipole will be in the direction of positive k cap. So we'll get the dipole moment as P, the magnitude is 7.5 into 10 power minus 8 into k cap. K is the z axis. Now we are going to our some question. An electric dipole with a dipole moment of 4 into 10 power minus 9 coulomb meter is aligned way at 30 degrees with the direction of a uniform electric field of magnitude 5 into 10 power 8 Newton per coulomb. Calculate the magnitude of the torque acting on the dipole. The given dipole moment is, the magnitude of dipole moment is 4 into 10 power 4 into 10 power minus 9 coulomb meter, and theta angle equal to 30 degrees. Angle is 30 degrees. And the electric field is equal to 5 into 10 power 4 Newton per coulomb. Yeah, now the torque acting equal to P bar cross E bar, which in return equal to P into E into cos theta. So as we have the value of P 4 into 10 power minus 9 and theta is 30 degrees and electric field is 5 into 10 power 4 Newton per coulomb. As we know that cos 30 is, sorry, P cos E P into sin theta. So sin 30 is 1 by 2. So we will finally we will get the value of torque is 10 power minus 4 Newton meter. A polythene piece rubbed with mole is found to have a negative charge of 3 into 10 power minus 7 coulomb. Estimate the number of electrons transferred from which to which. Yeah, first we will decide the direction of transfer of electrons. As the polythene piece has acquired a charge of 3 into 10 power minus negative charge of 3 into 10 power minus 7 coulomb. As the charge indicated by the polythene piece is negative, so the electrons are transferred into the polythene piece. So the polythene piece has acquired the negative charge. Estimate the number of electrons transferred. As we know that through the quantization of charge, Q is n into E by quantization of charge. So from this we will get the value of n equal to Q by charge of an electron. We have the value of charge of electron as 1.0. Given the value of charge acquired is Q equal to three into 10 power minus 7 coulomb. And we know that the charge of electron is 1.602 into 10 power minus 19 coulomb. So by using this, we will get the value as n equal to 1.87 into 10 power 2 into 10 power 2. Is there a transfer of mass from bool to polyethylene? Yes. As the electrons have transferred from bool to polyethylene, so the electrons also have some mass by like 1.6, 9.1 into 10 power 30 minus 31 kg. So some amount of mass is transferred to the bool. To insulated charge, if you want to find the mass of mass transfer, n equal to number of electrons transferred into mass of an electron. As you know, the mass of electron is 1.9.1 10 to the minus 31 kg. We can calculate the mass transfer. Two insulated charges, copper spheres A and B, have their centers separated by a distance of 50 centimeters. What is the mutual force of electrostatic repulsion in the charge? If the charge on each key 6.5 in 10 power minus 7 coulomb, the radii and the are negligible compared to the distance of separation. Yeah, you can use the formula F equal to KQ1 Q2 by R square. Yeah, we have the values Q1 and Q, like the both the charges are having the same forces, so the value of Q1 and Q2 will be same and equal to 6.5 into 10 power minus 7 10 power minus 17. And also the distance between the like R is given as 50 centimeters. So 0.5, like we will proceed with the SI unit. So 0.5 meters. So by solving this, we will get the force at 1.521 into 10 power minus 2 Newton. Yeah, we also have the B question. What is the force of repulsion if each sphere is charged double the above amount and the distance between them is half? Like initially, B part. As we have the formula F equal to KQ1 Q2 by R square. We substitute the value of Q1 as 2Q1 as the charge is double, both the charges are double. So and the distance between the two objects is half. The question if each sphere is charged double, the amount and the distance between them is half. So R becomes half by 2. So it will result in a it will become 16 times, like numerator 4 times and from denominator it's 1 by 4 in the denominator. It will come up in the numerator as 16 times the initial value. So it will result in the value 24.336 into 10 power minus 2 Newton. Now we will proceed with the 13th question. The figure shows tracks of three charge particles in a uniform electrostatic field. Give the signs of the three charges, which particle has the highest charge to mass ratio. Yeah, from the figure we can observe that both the like these are two plates. One is a positive plate and another is the negative plate. So the electric field will be in between the two plates will be from the positive to negative charge. Like in the down, it will be in the downward direction. So the two charges that are moved toward the positive charge will be the sign of will have the magnitude of negative charge, and the charge that is attracted toward the negative charge will be have the charge of positive charge. Has a charge of positive in it. So as the third charge is deflected more, deviated more from the two charges, the magnitude to the charge to mass ratio will be maximum for third charge. Now let's go to the 14th question. Consider a uniform electric field E equal to 3 into 10 power 3. What is the flux of this field through a square of 10 centimeters on a side whose plane is parallel to the YZ plane? Yeah, as you know that what is the flux of this field whose face of 10 centimeters? Like area of the square is 10 centimeters. At the side of the square is 10 centimeters. Area is a square. So area is equal to 10 centimeters means 0.1 meter. So 10 power minus 2 meters square. That is area of the square. And the electric field has a magnitude of equal to 3 into 10 power 3 Newton per meter, Newton per coulomb. So as you know, the flux phi equal to E bar dot dA bar. Here the flux and the electric field are perpendicular to the electric field is perpendicular to the surface. So the angle between the normal and the electric field is 0. So the flux linked with the surface will be E into A equal to 30 Newton per coulomb. 30 Newton meters square per coulomb. In the second case, the angle between the two planes is 60 degrees, and also we know that the flux equal to E bar dot dA equal to E into A into cos theta. Here theta is 60 degrees. So from substituting the values, we have the E value as 3 into 10 power minus 3 into 10 power 3 Newton per coulomb. and area is 10 power minus 2 meter square. And also we know that cos 60 is 1 by 2. We will get the value of 15 Newton meter square per coulomb. Let's go to the 15th question. What is the net flux of the uniform electric field through a cube of size 20 meters? Like the net flux linked with net flux through a closed body placed in a uniform electric field is zero. It is because the flux entering the body will through one surface will leave the flux through will leave the surface through the another surface. So the net flux linked with the body will be zero. So in this case also the electric field linked with this closed tube will be zero. Careful measurement of the electric field on the surface of a black box indicates that the net outward flux through the surface of the box is 8 into 10 cube Newton meter square. Given flux is 8 into 10 power 8 into 10 power 3 Newton meter square per coulomb. What is the net charge inside the box? As we know that flux equal to Q enclosed by charge enclosed by epsilon naught. Charge enclosed by epsilon naught. So Q enclosed will be flux into epsilon. The value of epsilon naught is, we have the value of the flux. The value of epsilon naught will be 8.825 into 10 power minus 4 into 10 power minus 4. So by using these both values, we can find the charge enclosed, which we will get as 7.08 into 10 power minus 8 coulomb. For part B, the net outward flux through the surface of the box was zero. Could you conclude that there were no charges inside the body? Yeah, like if the net enclosed, if the net flux linked with the body is zero, it signifies that Q enclosed is zero. So the net charge enclosed will be zero. So the sum of positive charges plus the magnitude of sum of the positive charges and the negative charge is equal to 0. It doesn't mean that there are no positive and negative charges. If we have if a body contains a 2 coulomb charge and a minus 2 coulomb negative charge, then the total flux linked with the body will be 0 as the net enclosed charge is 2 minus 2. The total sum of charge inside the body is 0. It doesn't mean that there is no charge present inside the body. So even the net flux enclosed by the body is 0. There may be the charge may be present inside the body. The point charge 10 microcoulomb at a distance of 5 centimeters directly above the center of a square of size 10 centimeters as shown in figure. What is the magnitude of electric flux through the square? Think of a square as a size. Yeah, for finding the flux linked with this square due to a small charge present at a distance of 5 centimeters. Let's symmetrically assume another face at a distance of 5 centimeters above the charge. It will be symmetrically between the two faces. So similarly, if we try to imagine a square enclosing all the similarly if we imagine a square, imagine a cube enclosing the charge at its center of the tube, then the flux linked by the every face will be equal as it is at a distance equidistant from all the faces. As the cube contains 6 faces, the flux enclosed by the total cube due to all these, the flux enclosed by a cube due to the charge at its center is q by epsilon naught. So it's due to the flux due to all the faces. So as the cube has 6 faces, so flux linked with a single face will be q by 6 epsilon naught. Q by 6 epsilon. So flux linked with the single face will be q by 6 epsilon. So by using the superposition principle, we find out the flux linked with the square surface, square face. The point charge of Q at center of a cube Gaussian surface, 9 centimeters. On inch, what is the net electric flux through the surface? As the charge of 2 microcoulomb is present, given charge Q equal to 2 microcoulomb. 1 micro means 10 power minus 6 coulomb. And the length of edge is 9 into 10 power 9 centimeters. So 9 into 10 power minus 2 meter. So for finding the What is the net electric flux through the circuit? And the flux enclosed by the body Q by epsilon. As the object is placed in the center of the body, we get the flux enclosed with Q by epsilon. And by calculating the flux, we can get the flux linked by the body 2.26 into 10 power 5 Newton meter square per coulomb. Like we have a small confusion whether the charge is placed at the center of the cubic Gaussian surface or at the center of the edge of the cubic Gaussian surface. Like this is for the center of the cubic Gaussian surface. If it's placed at the edge, center of the edge of the cubic Gaussian surface, then we will assume that we will take some we will take 4 cubes so that the body is covered by the all the 4 cubes. Then we will calculate the flux linked with the surface. A point charge causes a electric field of -1 into 10 power 10 cube Newton meter square per coulomb to pass through a spherical Gaussian surface of 10 centimeter radius centered on the charge. The radius of the Gaussian surface for doubled, how much flux would pass through the surface? Yeah, by changing the radius of the Gaussian surface, the flux linked by the object does not change because the flux linked will be dependent on whether the is irrespective of the radius shape of the Gaussian surface enclosed by the object. It only depends upon the charge enclosed by the surface and the medium in which it is placed. What is the value of the point charge? Yeah, as you know that given flux equal to flux, the symbol of flux is phi. Phi equal to 1 into 10 power 3 Newton meter square per coulomb. And also we know that the formula for flux equal to Q enclosed by epsilon. So by using this formula, Q enclosed equal to flux into E. We will get the value as minus 8.854 into 10 power -9 coulomb. Let's go to the 20th question. The conducting sphere of radius 10 centimeters has a unknown charge. The electric field 20 centimeters from the center of the sphere is 1.5 into 10 cube Newton per coulomb and points radially inwards. What is the net charge on the sphere? As it shows, the electric field is point inwards the radius, radially inwards. it means that the net electric charge inside the body is negative. As we know that the electric field due to only the negative charges will be pointing inward and the positive charge will be pointing outward. So we will now focus on the magnitude of charge. As we know that the formula for electric field is equal to kq by r square. We have the value of electric field is 1.5 into 10 cube, 10 cube Newton per coulomb. And the distance d, I mean, and the distance r equal to 20 centimeters, so 0.2 Newton, 0.2 meter, and the value of k is k equal to 9 into 10 power 9 Newton meter square per coulomb square. By using all the values, we can find the value of q. As we know the value of E, the value of K, and the value of R, we can get the value of Q. So we will get the magnitude of Q as 6.67, and also we know the charge of Q is negative, as we know that the electric field points radially inward, so the charge is negative, and the magnitude we can calculate from the formula 6.67 into 10 power minus 9 coulomb. We'll go to the 21st question. A uniformly charged conducting sphere of 2.4 meters diameter has a surface charge density of 80 millicoulomb per meter square. Find the charge on the sphere. What is the total charge electric flux leaving the surface of the sphere? Yeah, the diameter of the sphere is 2.4 meters, so the radius the diameter of the sphere is P equal to 2.4 meters, on the surface charge density sigma equal to 80 into 10 power minus 6 coulomb per meter square. So we know that charge equal to sigma into the area in which the charge is spread over. So area is pi r square, but we have the relation in diameter, so we will use as 4 into pi d square. Four pi r square. The area of a sphere is 4 pi r square, but we wrote it in terms of diameter, so The 2 gets cancelled and we will get the value of charge as by substituting the value of sigma and diameter d, we'll get the charge as 1447.646 into 10 power minus 6. 10 power minus 6 coulomb. And the part B, the flux. Flux linked is Q by epsilon naught. Q by epsilon naught equal to, by substituting the value of epsilon naught, you know that the value of epsilon naught will be 0.825 into 10 power minus 12, and the value of Q is 1.447. 0.674646 into 10 power minus 6 coulomb. We will get the value of flux is 164 into 10 power 6 Newton meter square per coulomb. Now let's go to the 22nd question. An infinite line charge produces an electric field of, given the value of electric field as 9 into 10 power 9 into 10 power 4 Newton per coulomb, and the distance d 2 centimeters, so 0.02 meter. As you know, the formula for electric field E equal to lambda by mean linear charge density. 2 into 2 pi naught into r. R is nothing but the distance. So by using this formula, we know the value of E. We know the value of E. Value of epsilon naught 8.825 into 10 power minus 12, and the distance V. So we can find the value of lambda, surface linear charge density. Lambda equal to 9.98 into 10 power minus 8 coulomb per meter. Linear charge density, so charge per unit length. Units will be charge per unit length. So we'll find the value of lambda from the power. We will now reach to the final question. Two large thin metal plates are parallel and close to each other on their interfaces. The plates have surface charge densities of opposite sides of magnitude 17 into 10 power minus 22 coulomb per meter square. What is in the outer region of the first plate, in the outer region of the second plate, between the plates? Yeah, now we are solving the final question. Let's take these are the two plates, and one has a charge of magnitude. The charge of they have the charge of Q equal to 17 into given the charge density, that is assume that Q is the charge density here, P is the charge density here. P equal to 17 into sigma. Let's check sigma as the charge density. Sigma equal to surface charge density is 1 equal to 17 into 10 power minus 22 coulomb per meter square. So sigma plus sigma, this is minus sigma. Now let us take the Gaussian surface as a bigger one. Including both the plates. If we find the, let us assume the electric field here will be E, and we find the area of the surface is dS. Then the total flux linked with this surface will be 2 into E into dS equal to total charge enclosed. The total charge enclosed will be sigma into dS minus sigma into dS. That will be minus sigma into dS by epsilon naught. This will become 0. So the electric field outside both the plates will become 0. The electric field outside both the fields both the plates will become 0. Let's take the field inside. Now let's take the Gaussian surface at this part. And here the electric field is E. The area is 0. And we found that the electric field is 0 outside the plate. So electric field here will be 0. So the flux linked with the Gaussian surface will be E into dS equal to E into dS equal to sigma into dS by epsilon naught, where ds just cancel, and the electric field will be sigma by epsilon naught. So from this we will conclude that if there are two plates with charge sigma on one surface and charge density minus sigma on the other, the electric field outside the plate will be 0, and the electric field in between the plates will be sigma by epsilon naught in this direction. Yeah. That's all with the questions today. Thank you for your